Good morning, everybody. And thank you for attending the second 2025 Applied AI Future Seminar Series, sponsored by the Dean in the College of Engineering. That is part of the Applied AI initiative that we have in the College of Engineering. The distinguished speaker today is Professor Sergei Kalinin, who is the Weston Fulton Chair Professor at the University of Tennessee in Knoxville. A former principal scientist at Amazon and longtime leader at the Oak Ridge National Laboratory, Professor Kalinin is a pioneer in applying machine learning and AI to material science. So we're going to have a really nice presentation in this area. The title of his presentation is AI, Microscopes, and the Quest for Better Materials. His research drives innovation in materials discovery, automated experimentation, and advanced microscopy. With over 650 publications and numerous prestigious awards, Professor Kalinin is a leading figure in this field. So please welcome Professor Sergei Kalinin.
Thank you very much for the invitation, and it's a great pleasure to be here. Special thanks for Dean for inviting and kind of making sure that this visit is possible. And thank all of you for coming and the opportunity to share some of the topics that we work in the field of applied AI, or in other words, how to make AI useful. So let me start with the statement that world is first and foremost the material opportunity, right? So whenever we talk about the world in general, we always think about how to make materials out of which we can build something else. How to make better cars, how to build energy storage, how to build photovoltaics, how to build better construction materials. And about 20 years ago, Gerd Sider and Dane Morgan paper was an inflection point which showed that we can combine the high-performing computers and machine learning in order to sort through theoretical domain and find the best material candidates. And for 20 years since then, this field has been developing almost exponentially, so to the tune of Google, Microsoft, and Meta now working in this field. But it's not enough to predict materials, right? So we cannot live in the house that's built out of the imagined bricks. We cannot drive the car which is powered by the imagined battery. At some point, we actually need to make things, and we need to make them with the right functionality. We need to be able to manufacture them, and we need to be able to manufacture them at cost. So the interesting time here now is that despite all this growth in the interest for machine learning over the last 20 years, despite all the successes of the machine learning in the areas such as drug design, material science remained relatively conservative. So if you think what you are doing in the lab now and what you have been doing in the lab 10 and 20 years ago, the answer would be roughly the same type of job. So material science cannot change overnight, but in fact, what's happening now comes very, very close. And the key to that, sort of to quote the Oppenheimer movie, the theory in machine learning can only get us so far. At some point, we need to bring the machine learning in the real world. So how can we do that? So obviously, I'm a material scientist and I'm an experimentalist. So when I joined University of Tennessee, Knoxville, it had a fairly long tradition of the automated experiments. So probably between North Carolina State, UT Knoxville, MIT, Santa Barbara, these are the places where the automated experiments started first. So some of my colleagues had something like 15-year history of the combinatorial synthesis and even combinatorial processing. So some of my other colleagues started in 2019 to work on the automated synthesis of hybrid perovskites, kind of starting from simple open-tron robot and moving to the robotic film deposition and in situ characterization. So when I joined UT, I worked with my colleagues to develop the automated scanning probe microscopy capabilities when we have the SPM tool that sends the data to the University of Tennessee supercomputer, analyzes return control commands to the instrument. So I worked with my colleagues to build the similar workflows for automated electron microscopy, and even things like automated nano-indentation, where rather than making mechanical properties everywhere, we have a computer vision algorithm that finds interesting locations and take indentation measurements there. And sometimes we can use it for studies, sometimes we can use it for fun. So this is the example of the amorphous silicon. This is the crystalline silicon, and we can use the electron beam of the microscope as the 3D printer to essentially create crystalline material atom by atom. So think about it as 3D printing on the atomic level. And there are clear ways to automate things like automated X-ray, polymer flow synthesis, and so on and so forth. And then the question becomes that, okay, we have these autonomous tools. So some of the tools are autonomous, some of the tools are still human operated, but the key thing is, how are we going to make it work all together, and what practical value does AI bring to us as experimentalists? And here we're coming at the time when situation is interesting, right? So we all know that AI is going to take all our jobs, right? However, when it comes to washing dishes, I still have to do it myself. So ChatGPT is not going to do that. So there is a history of very loud predictions, right? So the whole idea of getting human out of the loop started barely 10 years ago. So folks like Hinton, who obviously invented AI and got Nobel Prize for a very good reason, is also, in addition to building modern ML, also has a history of predicting that machine learning is going to substitute radiologists. Or a year ago, we all have been concerned that AI is going to kill all of us, and now nobody remembers it anymore. So interestingly enough, a lot of predictions about what AI is going to do and not going to do haven't happened yet, or at least happening much slower than it was advertised. And in some sense, with the things like ChatGPT, things become even more weird, right? So we consider ChatGPT as something that can help us. Sometimes we consider it as an extended version of the Google search. But there are already companies out there that basically say, hey, we can make automated scientist that's going to produce a scientific paper at the average cost of $15 per paper. And then, of course, the question becomes, okay, it's not like the scientists' result of science is publications. So if we produce papers at $15 per pop, who is going to read these papers, and what value do they bring in the first place? So the question becomes, how can we cut through this hype about the machine learning and find out what it is practically useful for? And I guess the idea here is that we need to separate two things. One is making decisions, which is something that typically human make and AI can help with. And another is the execution of decisions that can be done by humans and automated experimentation. So once we think about AI, it's not a magic idea that whatever we can think about or aspire to instantly becomes reality. When we start to think about the practicalities of getting stuff done, then hype basically disappears. It becomes a question, what decisions can be executed? Essentially, it's a question, what type of equipment do I have in my lab? So how fast they can be made? Am I talking about something that I can do in a second, or is it something that I have to work on for several hours or weeks? So the same thing about the execution of the decisions. Same thing applies to the improving the decisions. And another very interesting thing is that our colleagues in the ECS world always talk about AI idea of making hypotheses, and that's super important. AI can really help us develop scientific ideas. But the problem is that for each hypothesis, we need to define the corresponding experimental action space. How can this hypothesis be transferred into the reality? And that's the part which is not going to come from the computer science community. It's the part that can be done only in the domain communities. So how does it all apply for material science? So let's look at what we have at this point. So on the one end, we have the theory workflows. So this is something that started almost 20 years ago. By now, it is a mainstream of the AI for materials and chemistry. And generally, these workflows are all structures about defining some search space, going through the sequence of progressively more precise filters, and then coming up with some candidates for the experimental validation. It's a great foundation to build upon. But that's absolutely not how science works. In science, in the real science, we always make stuff, and then based on what we made, we close this feedback loop to improve our models. So why is it difficult? It's difficult because very often these workflows start from DFT or MD. We obviously are not going to improve DFT and MD from based on the results of the single experiment. We need something in between. So on the experimental side, we work with the state of the art is the Bayesian optimization workflows. So basically what it means is that we have some parameter space. So think about phase diagram or processing space or whatever. We synthesize material at one conditions. We take our physical measurement. So very important thing is that we need to figure out what is that about the measurement that we care about. It's a very complex task because, for example, if you make materials for batteries, sometimes you care about the phase purity, or for example, what phase you made, for example, the lattice parameters. And sometimes you care about the peak widths, which connect somehow to the crystallinity of the material. And sometimes you will care about the presence of some second phase that you know is going to very deleteriously affect the properties of your material. So in other words, our measurements are usually multimodal and give very high dimensional data sets. What we care about in this particular measurement is highly domain specific, and there is a whole art of figuring out what is that we want to look at. But once we've done it, we can create a surrogate model. Surrogate model basically allows us to interpolate over the whole parameter space and interpolate with giving the uncertainty in prediction. And then we figure out how aggressively we want to go about optimization. If we have a long time in front of us, a lot of experimental cycles, we can go exploratory. If we have only 3 experimental attempts, because after that we run out of our experimental budget, we go for greedy type of policies. And then we kind of continue this loop. So this is the case where I have stolen an example from Professor Ahmadi lab. So since, for obvious reasons, a lot of work I do is related to building ML workflows for synthesis of hybrid perovskites. And what this image illustrates is that for all of you that work in the experimental sciences, you can clearly realize that the way the decisions are made in the experimental lab are much more complex than single optimization. It's true that funding agencies such as DOE or NSF ask us to work on the hypothesis-driven science. That's how we write proposals. What we are doing in the labs is almost always optimization, to optimize the yield, to find the better materials. So the hypothesis-driven science is underpinned by 99.9% effort in optimization. But this optimization is not a single loop. That's what usually a very mature industry works on. What we work on is multiple connected loops when we use the same end members to make microcrystals. We use the data from the microcrystals to choose the films. We take the measurements of the structure functionalities, and then somehow we interpret the data streaming from the instruments in terms of the underpinning physical mechanisms. And then we choose different end members in order to address the phase evolution. So some of these decisions can be handled by the machine learning. Some of these decisions require very deep understanding of the physics of the system and microstructure formation, and only by understanding this physics, we would be able to make better decisions in the lab. And generally, it applies to pretty much everything. So anything that we deal with starts with the fundamental research, often informed by theory. It essentially should end up being a product, but these optimization cycles are fast. These are incredibly slow, but nonetheless, functional knowledge is developed in the lab. The value propagates from the real-world deployment. And it takes a lot of human intuition in order to connect these multiple cycles. So the question becomes, going back to the AI, is that whether the machine learning can help us to build those connections. There are many aspects to it. Some of them are decision-making, some of them are operation. So there is a very well-known Moravec's paradox that it's easier to simulate the climate than to make a robot that makes a toaster. But you know, the most important thing here is that the robot doesn't need a toast. I do need a toast. So if you think about everything that machine learning is doing now, you can have a feeling that there is a part that is missing. So machine learning is about data, right? We know that. We also know that there is physics, and in fact, there is a continuum of methods between the purely data-driven and purely physics-driven. But the question becomes not only how, but why. And the part that is missing in this diagram is essentially what is our driving force. So what are the rewards? So for example, sometimes we run our experiments in order to make a better energy material. Sometimes we want to make a better energy storage. Sometimes we want to improve manufacturability. So these are very, very complex objectives. The rewards that are used either in ML and physics are much more simplistic. For example, if we work with the data-driven methods, we typically minimize some form of loss function, right? So what's the relationship between the loss function I use to train the neural network and making a better energy material? It's not a simple thing. So in physics, our reward functions are usually predictive power of the model or simplicity, right? So if we have the answer in the form of the short symbolic expression, we intuitively feel that this is right. This, of course, works in fundamental physics. It actually doesn't work in the condensed matter physics that well. This one is usually much more complicated. But again, there is a big difference between Hubbard model and the high temperature superconductivity. And therefore, the question that I asked is maybe, just maybe, in addition to learning how to use ML method, we also need to focus on the rewards, why we are applying certain methods in the real life. And as an example of this, probably the world's strongest confirmation bias, you can ask a question of, okay, what does this guy know about machine learning? But this is the quote from the book by Peter Norvig, who obviously knows everything about machine learning. And the introduction from this book basically has a very golden statement that until now, virtually all ML has been about solving the problems where a reward or optimization function is known. So the point that I want to make is that in the real world application, the optimization function or rewards are unknown. And therefore, the interesting direction for research becomes, what if we, for the time being, forget a little bit, forget about data? What if we forget about the algorithms and focus our attention on the reward? Why are we running some form of ML workflows? So kind of to follow the Thomas Kuhn book, if you have a new brilliant theory and you think that it is useful, there are two things, at least two criteria that this theory should satisfy. One, it should be consistent with the previous observations, at least the majority of them. And secondly, this theory have to allow you before or further than the current state of the art. So obviously, since my field, preferred field is microscopy, let's see how this reward-based approach works for building autonomous microscopies and autonomous material synthesis tools. So for me, this journey started quite a while ago. So my first paper is talking about the thinking microscope appeared about 15 years ago or more. And I have been working on applications of ML in the different problems in the experimental sciences for quite a while. So, and maybe for the last 6 years or so, I have been focused on using machine learning to build the autonomous characterization tools. So based on this experience, it is possible to sort of qualify the levels of the machine learning development in microscopy and generally in all kinds of physical characterization. So the first level in this case, imagine that we run a day in the microscope, we get some data, and then we analyze it after the data is already acquired. So the most natural way of data analytics. So the second level is when we have the microscope running in real time, and the machine learning operates in real time to help you analyze the data. For example, represented in the form which is better tuned to the human perception. For example, if the data is very high dimensional, or if the data is just sampled at a very large number of points. However, at this level, the decisions are still made and orchestrated by humans. So there is a human in front of the instrument that looks at the screen, makes decisions, and types the new command. So the third level of ML application is when the machine learning agent gets access to the data stream coming from the microscope, makes decision, and can execute these decisions directly on the instrument. So this is where we talk about the autonomous agent connected to the physical world. There are two more levels. So one is learning physics contained in the data, both based on the microscopy data and the general knowledge. And the most interesting one, and that's something that my group works on now, is the upstream experiment planning, when the microscope analyzes a specific sample and then tells the synthesis robot upstream what next sample to make. So the question becomes, how can we, let's talk about this level of agency. So the question becomes, how does human makes decisions when the human is in front of the microscope? And what's interesting is that, you know, the principle of the Japanese poetry, right? So when you have a tanka, you have a very small expressive language that allows you to reflect fairly complex thoughts and perceptions. There is a price for this, right? So the Japanese poetry is beautiful, but without being an expert in the, for example, the art during the Heian period, it's impossible to understand it. So typically for each tanka, there is 3 pages of short explanations and 30 pages of the long explanations, without which it is impossible to understand it. So when the human runs the microscope, it's almost the same scenario, because the number of operations that human can make sitting in front of the microscope is actually very limited. You can tune the microscope, you can find a region of interest, you can take some spectroscopy, you can tune things a little bit more, and you do it over and over again. I suspect that this is the same thing when you work on making next battery materials or growing the film, whatever, but since I have never done it, I can only speculate it. But for microscopy, that's kind of my direct experience. And what's interesting is to analyze the logic behind the human decision-making during operation of the microscope, or in other words, understand the reward structure. And it turns out that if you do that in the beginning, your operation would be focused on optimizing the microscope to make it work better. Then it is very common to explore the unknown object names based on the statistics. And after that, based on the curiosity, for example, if you see some form of unusual structures, you can decide that this is something that I want to look at in detail. And only after that, we start to explore something on the level of the deep physics decision-making. For example, if I want to understand the physics of the ferroelectric walls and the role of the flex electric effects, I can decide that this region is particularly interesting. But if my role is to understand something related to the disclination behavior, I will say that these regions are interesting. So the interesting thing here is that even though the operations we can execute on the microscope are the same, the reward function that we have in front of shifts throughout the experiment. So our motivation changes, which in turn tells us that if we want to build the autonomous tools, what we have to do is to represent the operation as a tool, as a sequence of commands. So this is our workflow. And then there are several ways we can bring the ML into play. So we can define the policies. Policy basically means that we have a lookup table. If this is what you see on the screen, this is what you should do. Fixed policy type of workflows are fully adequate to fields like semiconductor manufacturing, because these fields usually come with a long history and mature, well-built databases. So there is a strong level of prescription of what is that you want to accomplish. For more open research, it's not going to work, right? So if I know what to do, that means that I already pretty much know everything. So it's not enough. So if we want to build the autonomous tools for exploration, we need to define the rewards, and the policies has to be learned while pursuing those rewards. If the rewards are available at each step, these are myopic workflows. This is what we can do with the Bayesian optimization. If the rewards are sparse, then this is more complex. This is where we require reinforcement learning or A-star or Monte Carlo tree searches. But if we don't have rewards, if we only have objective, then machine learning simply does not apply. I cannot build a microscope workflow that will make a better battery. I can only build a microscope workflow that will study the degradation mechanism in a given battery as long as this degradation mechanism can be learned from observation. If it cannot be learned from observation, that it requires alternative studies that either this alternative studies has to be a part of the discovery loop or it cannot be accomplished. So the reason why it is important is that, as we discussed, if the rewards are defined, then we can fall back onto the last 20 years of development in machine learning and make it happen. If the rewards are not defined, meaning we don't know what we want to get out of the experiment, machine learning is not going to help us. So how does it work for imaging? Well, the good thing is that going back through the publications, my own experience, and talking to my colleagues in microscopy field, the reward functions, I mean, there are a lot of them. Of course, they vary, but many of them are reasonably well defined. So some of them are imaging optimization. We always want to make our instruments work better. But for material scientists, optimized imaging is not a goal for itself. So unless you're a microscope manufacturer and you sell microscopes, or unless you do something with totally new tool and you want to publish a paper in Science, most of the time, imaging optimization is not the ultimate goal. It's a step to being able to understand what happens inside the material. So there are reward functions associated with the physical law discovery. So this one is super interesting, but remember my statement that for each hypothesis, we need to have the experimental footprint sufficient to check it. There are not that many hypotheses that can be verified only within a microscope. Most hypotheses require much more. Synthesis, modeling, characterization, all taken together. But there are some that can be realized only within the microscope. And then there are a lot of intermediate rewards associated with the image analysis, learning structure property relationships, and so on and so forth. And then if we start to think about it, then we realize that pretty much you can take any publication in electron microscopy over since the Ernst Ruska time, and you can clearly formulate what were the reward and what were the objective. The objective is something that we write in the introduction. The reward is something where the technical discussion stops. That's what has been accomplished. And with this understanding, it has become possible to be much more systematic about how we build the autonomous experiment workflows. So this is the example of the Spectra 300 at UT. So this is the gold nanoparticles and titania. So what we do here is we take the image, we send it to the supercomputer, or it can be any cloud resource. We use the commercial Foundation SEM model to do the segmentation, and then we can tell the microscope to go through the particles one particle at a time, and take the EDS diffraction and yields. So from this particle, then we take it from the next particle, and so on and so forth. So what is the reward here? If I was doing it manually, that would be a lot of point and click. If I were doing it on the grid, then a lot of my measurements would be from locations that I'm not particularly interested in. So in this case, I have an example of the predefined policy. Take the measurement on one particle at a time, and my gain is the efficiency of the data collection. In one experiment, I can collect data from several thousands of particles, as opposed to several tens of particles. So depends on what is the downstream use of it is, but we can provide a clear indication of what the gain is. So this is another example of the fixed reward policy. So the work that we have done when I was still at ORNL, when we try to understand the switching of the ferroelectric material. So why is it possible? It is possible because for the switching of the ferroelectric material, the experimental footprint required to check the hypothesis is just one instrument. I don't need anything else. I just have a sample, and what I want to control is the parameters of the bias pulse that I apply to the instrument. So if this works, then my parameters hypothesis space is relatively small. This is just two-dimensional. My hypothesis, so at that time they came out of the domain experience. Now they, in principle, can be formulated using the large language models. And what the microscope does, it basically figures out which hypothesis is the correct one. So you can see that the hypothesis number 3 shows the best score. That basically means that this hypothesis is the best descriptive of the polarization switching process inside the material. So once we move to, so this is kind of the example of several workflows that we run at UT now. So this is the example of the autonomous tuning of the instrument. So it actually turned out to be kind of interesting because originally we thought that if we want to use IFIM for materials discovery, we need to focus on certain set of operations. And then we realized that you also have to constantly tune and tweak the microscope. So you cannot build a just a workflow that do it. So the material imaging optimization has to be a part of it. But once it works, we can basically repeat any type of experiment that we can configure. We can tune the microscope. We can discover structure-property relationship. That's a simple experiment when we find objects of interest and take the measurements only on this project of interest. And once we have these building blocks, we can actually switch to the more complex experiments where we start to use microscope to explore the combinatorial libraries. So why is it interesting? So it's interesting because combinatorial libraries have been around for a long time, so almost for 60 years. And the value proposition of the combinatorial library is that you can make a sample that has multiple compositions, so some cross-section across the phase diagram, and you can make it in one shot as opposed to making multiple samples. So why did combinatorial libraries remain a niche area for a long, long time? Very simple, because making material is important, but after it is made, you need to characterize it. And if making the material takes half a day and the characterization takes several days, then by making combinatorial library, you don't expect anything. So if you make materials 50 times more efficient, but your characterization takes 3 times longer than synthesis, then your total gain becomes something like 10%. You really don't win much. So combinatorial libraries will remain a niche method unless we can characterize them. So guess what? For certain material systems, for example, for ferroelectrics, for photovoltaics, for certain classes of energy storage materials, scanning probe microscopy is the easiest way to probe their functionality. However, scanning probe microscope is, of course, cheaper than electron microscope, but much more complex to operate on the level of real sample operation. So in order to build the workflow to study combinatorial libraries, we have to look at the optical image to make sure that we don't slam our tip into the surface and destroy it. We have to add the automated tuning of the instrument for topographic imaging and for acquiring the spectroscopy. And on top of it, we need to actually create the exploration workflow that approaches the surface in one place, takes the measurements, withdraws the tip, moves several millimeters to a different location, takes the measurement in another location, and so on. But in the end, it worked. So for example, what you see here, it looks like a typical Gaussian process, and in fact it is, except that at each point in this Gaussian process is basically the measurement of the real instrument, and this is the measurement that has been preceded by the tuning. So now we can take a library, so it can be a centimeter size, it can be a 5-inch wafer, we put it in the microscope, we turn it on, and then we come back in 24 hours when the measurements have been taken. And again, we can quantify the benchmark here. So yes, human can do that. But human will do it 3 times slower, and at least officially, humans are supposed to work 8 hours a day. The instrument can work 24 hours a day. So our benchmark in terms of discovery rate for binary and ternary libraries is about factor of 10. Does it matter? Yes, it does, because the principle is that if you want AI to do something, you have to do it manually many times before AI can do it for you. So yes, we know that we can explore combinatorial library manually, and it takes maybe 2 days. But we will never be able to explore ternary or more complex libraries using the human exploration. But with AI, we can now do that. And then going further, we started to realize that in addition to using the tools, we actually also need to focus our attention of how we infer knowledge from the data that we get. So very often, our instruments give us very cool data sets. So for example, for the same combinatorial library, we can visualize it using the electron microscopy and see that here we have ferroelectric domains, here we don't have ferroelectric domains, here we have something else, something interesting. We can use the scanning probe microscopy data in order to help us where to take the locations for far more expensive electron microscopy data sets. So this is a classical multi-fidelity schemes. But the key question becomes, how do we learn the physics from data? So obviously, this is not just blobs, right? So if you show this for a person who doesn't have any domain background on ferroelectrics, you'll say that this is blobs. If you are focusing on the ferroelectric materials, you start to realize that this is a phase separation in the morphotropic phase boundary system. So again, if I look at the data, for example, from the CL measurements or for the battery cycling or whatever, the level of understanding that I will have not being an expert in the field and the level of understanding and therefore capability to make decisions from the expert of the field would be very different. And therefore, the question becomes, can we improve the understanding of the imaging data, and can we do it in the unsupervised manner? So why unsupervised or weakly supervised? Because if I understand the data only after the experiment, I generally cannot go back and run experiment differently. There is a big incentive for us to be able to analyze the data on progressively deeper level of understanding while we are still running the instrument, so that our understanding affects the way that we run the experiment. So if we do it afterwards, okay, it's done. But if we do it during, and if we can make better decisions during experiment, then AI really starts to pay off. So how can we do that? So for example, here the interesting analogy is the classical before LLM natural language processing. So when you take the sequence of symbols, and then you progressively interpret them as in terms of the semantic segmentation, you find words, you find the parts of speech, and then you start to basically take a sequence of symbols and basically uncover the meaning behind them. So now we don't see many of that because LLMs basically took over, and to some extent it solves the same problems, to some extent it kind of creates new ones, but we don't have anything equivalent for the images. So we typically take images, we clean images, we did some form of key point and descriptor analysis, but we almost never go to physics analysis to learn the physics behind images. And the question becomes, can the reward-based workflows help us to do some of the parts of this workflow? So not manual analysis of data, but do it automatically. So a simple example from the same bismuth ferrite images. So this is the electron microscopy data set. This is how the data will look like if we use our knowledge of physics to visualize the order parameter field in the polarization. So in this case, we start with very biased physical model. We applied it to our data, and we obtained the data in terms of this physical model. Of course, it's a strong regularizer, and it's a biased regularizer. Therefore, all other physics that was there got thrown away. We find only what we look for. Can we use the unsupervised machine learning method to find what else is there in the data? And it's a very simple example. Yes, we can. But in order to use even unsupervised machine learning, we need to define our descriptors. And if my descriptor looks like this, and this, the answer is going to be totally different. So the question is which one? So this one seems plausible because it looks like a ground truth. But again, ground truth already means that I have a preconceived notion of what happens in my system. So do I see something interesting here? So what's the difference between this one and this one? Can I somehow do it in the way that is principled and fair? And fair in the sense of kind of fair principles. And it turns out that this type of image analysis is absolutely universal. You do it in scanning probe microscopy, you do it in electron microscopy, you do it in bio and medicine, and so on and so forth. So we always start with the data and go through a very complex set of operations to find out what's inside it. So the problem with this workflow is that they're complex, and the problem with this workflows is that they're non-myopic. So depending on how we make decisions here, the answers at this stage can change, and very often that requires multiple weeks analyzing the data. So we ask the question, rather than doing this type of analysis with the pure human decision-making, can this reward-driven concept allow us to build this analysis workflows in real time? How would we do that? Very simple. We define the reward. Are we doing anything wrong or biased by defining the reward? I mean, you can argue yes, but first of all, reward very often is based on the fundamental physics consideration. So in this case, it's subjective. And secondly, reward is always traceable. I can say that in order to understand the physics in this image, these are the assumptions that I'm making about the system, and this is how I construct my reward function. And then given this reward function, my workflow, meaning the sequence of operations and the hyperparameter of this each operation, would be optimal. Your reward function can be different, but then we can compare apples to apples as opposed to I think so versus you think so. So does it work? So it turns out what's the value proposition? Well, the value proposition in this case that we go from human labeling, sensitive to distribution tip and black box method to unsupervised, robust, and explainable. But then would it work? So let's look at the same ferroelectric domains. So what can be the reward function for the image segmentation problem if I want to find ferroelectric domains? Very simple. From basic thermodynamics, I know that the walls want to minimize their length, right? Walls come with energy, and energy wants to be minimized. Second consideration is that I know that based on the crystallographic consideration, the wall should be straight or close to straight. So the thing is that I don't know the true balance between the two. I don't know how much I should favor the length versus straightness. But that basically means that I can solve the problem of the multi-objective optimization. So I can construct a Pareto front. And then for this part of the Pareto front, this is how my segmentation look like. For this part of the Pareto front, this is how the segmentation look like. So, I mean, in this particular case, I happen to know that this is the result of the Mistilt effect. So this is not a material physics. This is the result of the imaging. But once I have this optimal segmentation, then I can start to do hypothesis testing. What is the mechanism? How much I believe it? What is the statistical criteria? So basically, I connect the image analysis to the very well-established mechanism of the classical discovery science. And it turns out that, again, our dream was to make it in real time, and it worked. So this is the example of the real-time reward-driven discovery workflow that runs on the real instrument. And the interesting thing here is that we were able to benchmark it against the neural network solutions. I want to be very careful about it because if I benchmark the approach that my group developed 6 years ago against the approach that my group developed a year ago using the benchmark that my group developed, that becomes a little bit like a award ceremony in North Korea. But nonetheless, it's important to start somewhere, and at least within our experience, these methods work at least as well for simple tasks as the DCNNs, and it seems like they're less sensitive to noise because we incorporate the physical biases or physical inferences in the form, in the objective form. Now, why else is the reward approach useful? It is useful because it allows us to build the human-in-the-loop intervention. So let me show how it can be done. So again, this is a still Oak Ridge result when we have autonomous experiment trying to map the nonlinearity in ferroelectric films. So in this case, you can see the active exploration. Then the algorithm decides that it wants to get stuck here. So maybe this is an interesting region, or maybe something wrong with our ML algorithm. So this is the example when the algorithm clearly decides to get stuck in these two locations. So what's going on? Well, the idea is very simple. So in conventional experiment, human makes all the decisions and implements them. In the examples of the autonomous experiment that I've shown you, on the previous one, the human formulates the policy hyperparameters, and then these policy hyperparameters are communicated to the machine learning agent, and then they don't change during the experiment. And we don't know whether they're optimal or not, because when we typically do machine learning, we always spend a lot of time tuning on the test set and then on the validation set, and then we test. In the active learning, when our machine learning agent interacts with the real world, we of course don't have test set and we don't have validation sets. Somehow we need to be able to ascertain where things are working right or not. So in some sense, if our hyperparameters are fixed, it's like we sit in the car, we choose the direction, we press the accelerator, and we don't turn the wheel. So if the direction is correct and the road is straight, we are going to get very far. If the direction is chosen incorrectly or the road bends, we'll get out of the road very fast. So point is that we have to control the car, and we need to see what goes on. So the interesting thing is that when we run the automated experiments, it's not a problem for us to control the progression of the instrument. So the great thing that we have in experimental physical sciences, whether it is microscopy or synthesis or what's not, is that we don't have a problem of monitoring. Our state of the art is that human sees what happens in the lab, and makes decisions about whether things are going in the right way or wrong way. Unlike most of the machine learning where alignment is a problem and monitoring is a problem, for us it is not. However, the question becomes how can we tune the behavior of the machine learning agent? And then it turns out that if we have the standard myopic optimization loops, the most natural way for us to affect the behavior of machine learning agent is by changing the reward definition. So if I define this reward saying that, for example, this is the physics that I'm interested in, and the experiment clearly goes in the wrong direction, I can change my reward definition in real time. If I also can change the policies of the agent, so I can make it more greedy, so trying to find the optimal as fast as possible, or make it more exploratory. And this is, I'll also illustrate it, but it's also an option where we can implement the large language models, because the clear way forward is the transition from the shallow data-driven decision-making to the deep decision-making that is informed not only by data, but knowledge of physics, simulations, and so on and so forth. And the great thing is that the myopic optimization workflows allow very straightforward substitution of simple data-driven models, but much more complex physics-informed ones. So does it work? So it does. So obviously, academic environment is not where you build a polished product, but this is the example of the human-in-the-loop machine learning agent that runs experiment on spectra. So what you see here is that we run the experiment for a certain number of steps, and then the human changes the definition of the reward, and the type of the points that the agent explores become different. So where are we now? So I think that we are at a very, very interesting crossover point in experimental sciences. So our current generation of tools is human interacting with the microscope. So human has access to the data streaming from the instrument, and human introduces the basic commands, like take these measurements, tune the instrument, what's not. So what our team has built is the example of the machine learning agent that has access to the imaging and spectral data and issues commands. So we've done it for SPM. In my group, we've done it for STEM with Bill Busher. We did it with for the nano-indentation for folks in the mother group. But it's fairly straightforward to extend it for things like X-ray, synthesis, and so on and so forth. So human, in this case, of course, can interfere in the microscope operation directly, but the primary role of human is to observe the behavior of the machine learning agent and tune its behavior. What is the value proposition? Why would we want to do that? So the value proposition here is that electron microscopes are much faster than humans. So we can execute commands at the 10 millisecond level or even faster. Obviously, humans can execute commands on the level of make decision and execute commands on the level of seconds. Even though when I see my kids playing Smash Brothers or Ultimate Doom, I can say that it's probably a third of the second for them, but I'm much less successful in that regard. Also, it's much more fun to play Doom than work on the microscope, so forgive me, right? So anyway, in this case, it is entirely possible that machine learning agent makes not as good decisions as human. But then the question becomes, are we better off making 100 suboptimal decisions or one optimal decision? And at least for the electron microscopy, given the volumes of data it can create, I think we are moving in the fundamentally new area of opportunities here. And the great thing is that we typically lack a good connection between what we are doing in the lab and all the advanced capabilities induced by the large language models and so on and so forth. So as I mentioned, in this case, the operation of the ML agent is driven by the reward function. It's usually a lot of headache to formulate the reward function, but even in our limited experience of our group, LLM can assist here. And a very pleasant discovery for me was that for the last year or so, folks in Google actually start to work on the reward engineering, which basically means that we finally have this bridge between the mainstream machine learning with all the trillions of dollars put into ML and the type of things that we are doing in the lab. And this bridge matters because then we get to capitalize on the really high-end technology. So how does it apply for ways forward? So first of all, big data is super important. However, the big data by definition applies to the mature field, like semiconductor manufacturing, medicine, autonomous driving. It really doesn't apply that well for fundamental discovery research. By definition, big data means that we have a good sampling of certain parameter space. Discovery science means that we boldly go to where no one has gone before. We cannot have big data about the things that we don't know. However, what we do know is that each scientific field has its own strategy of dealing with the unknown. So if I put machine learning agent based on supervised ML to learn how to run IFIM, it's not going to be successful because each time it's a new sample. Humans somehow learn how to transfer their know-how over a very short number of iterations. Like compare all the data that went into building Waymo cars work versus how fast the teenagers learn how to run the car. Humans learn at the minuscule fraction of data than the best machine learning algorithms per se. So the reward functions, if we manage to formulate them, allow us to transfer at least some of the human skill set. I don't think it will ever exceed human expert, but it can considerably shorten the pathway to the human beginner in terms of how to start to do simple experiments. The LLMs are probably going to help us to get there. Why does it matter for the future? Well, as I mentioned to several times, I worked in a very interesting place in Amazon that allows you to think about the future. And one of the important things is that current industry was launched by IT, data, and AI leveraging real-world ecosystem. Amazon is essentially a combination of IT and essentially mail orders, right? It just grew to be a mail company, among other things. So things like Uber or Lyft is IT leveraging extra transportation capacity. Airbnb is IT and the availability of internet no matter where we go to leverage extra housing capacity. So one point that I want to make is that the opportunities to leverage existing extra physical world capacity are gone. They all have been used to this moment. There would be no next Amazon, there would be no next Google, there would be no next Facebook. What happens now is that these companies build an outstanding effort in the AI, and now the time for this AI to go in the real world and stimulate new industries in the real world. It's not going to be one super company, so real world is much more heterogeneous and time-consuming and dirty and hands-on and so on and so forth. But there would be plenty of opportunities like that. They would be different in energy, they would be different in constructions, they would be different in agriculture and so on and so forth. And the space of opportunity is how does it affect education? Here things are very, very interesting because 2012, 2014 was the time that industry was hiring anyone who can program. And a lot of people with the DFT, MD, and so on background went to work on deep learning. So many of them are now coming back to their domain areas. So the number of startups working in the field of ML-based chemical or materials design is now extreme. For the last year and a half, there are even startups that actually start to talk about experiment, not only about data, like Lila Scientific with the 200 mil startup and so on and so forth. It's also interesting that the value created by AI by now is actually fairly small. So the return of investment is something like 1%. And it's also interesting that Amazon or Google are not going to build their material science labs. They're going to seek interaction with the big research centers in order to build a partnership where the domain expertise and hands-on expertise comes from places where it exists, and the IT expertise come from industry. That's already happening. So Google partners with the Lab. Meta starts to talk very seriously with the Acceleration Consortium. So Microsoft partnered with the PNNL. I think that is a starting position. So obviously, AI is agnostic. Everything related to materials is usually kind of specific. If you work on the hybrid perovskites, you are not working on energy. And if you're working on energy, you are not working on the high entropy alloys for nuclear reactors. So we can expect that there would be a model going forward for the big IT industry interested in bringing AI to the real world to integrate with the centers of the domain knowledge that will allow to build this connection. And in order to make this happen, it has to be part of education. People have to have the hands-on skills that allow them to use ML in the real world, and that's the opportunity. And then just to end on a slightly more funny note is we can also speculate how this future will look like. So we already have humans interacting with ML agents, right? So that's already happening. The future is clearly multiple humans interacting with multiple ML agents, taking some form of decisions, competing for resources, right? You always have to have money to get stuff done, learning. So if you put all this element together, it awfully looks like that the future is going to look like a giant computer game. So that's exactly the models that I develop here. And again, this of course is a joke, but for example, our colleagues in the University of Washington already have a center of the gamification of scientific research, so who knows? Thank you.
Thank you very much, Professor Kalinin. Anybody that has questions, please let me know and I can bring the microphone to you. Yes.
I'm not really expert in microscopy, but I'm curious if you could use human decisions as examples and use some like inverse reinforcement learning about functions. Is it something
It's a very good question, and theoretically, yes. Practically, probably no. So the reason why I'm saying that is that human decision-making is usually very degenerate in terms of the reward functions. So we make decisions that have to be expressed in a relatively simple operations based on very complex decision-making process. So for example, the standard inverse reinforcement learning data sets have to operate with a very large data volumes for relatively simple decisions. So for human, especially human scientists working on the instrument, decision-making process is very complicated, so the complexity is large, and the number of training example is very, very small. So if I were working for Thermo Fisher or Oxford, I would probably think about using the monitoring data from the instruments to build the better ways to operate it. Working in academic lab, things don't work this way. So the best we can do is the bootstrap the decision-making by tracing the workflow when the human runs on the instrument, and basically record the reasons why we make certain decision to the LLM, and then try to distill the principle for decision-making at this stage. So if it is a bootstrap approach, at least based on the anecdotal and evidence, meaning that I tried it for 2 weekends and it seems like it may work, it may be a way forward. But standard inverse reinforcement learning, probably forget about it.
Thank you so much for this wonderful talk. I would like to ask one particular question about your examples that you were showing related to IFIM measurements. If you work with the most up-to-date machines from Oxford, right, newest versions of the software, they try to incorporate to some extent this AI optimization, right? When you try automatically approach, fine-tuning, all these things, right? But to some extent, it's going to be supplied as a black box, I assume, right? So they do not open like the code, they do not allow you to see like what is happening inside, right?
To some extent, yes.
Yeah, and like what is your vision like when you create your model? Do you want to kind of exclude this part of the software that is supplied, or you try to make them to interact to see if it's possible? Like what is your vision?
So generally, obviously, I'm not have no intention to compete with industry just because it's basically useless. But look at it this way: industry is interested in solving problems which are agnostic for the users. So agnostic of the use case. So better resolution, better stability, faster tuning. Humans each try to solve their specific problem using the microscope. So industry, by definition, cannot provide ML solutions that can be tuned, that can serve individual users just because all the users are different. So the type of ML that my team works on is this empty space between what industry provides, because, again, industry cares only what they have to bring so that the instrument is bought, and what the users are needed. So in some sense, when we work with Oxford or Thermo Fisher, our ask is give us the controls equivalent to the ones that human operator will have access to. So we don't need control on the aberration correction. I mean, you guys do that. We don't need the control of the low-level control of the single processing in IFM. We just need access to the same commands that are open for the human operator. It's obviously great to do it with the Thermo Fisher because they have API for that. It's a little bit more headache to do it with Oxford because they give you a collection of commands and you're welcome to build your own APIs. But you know, by now there are Python libraries that basically can take the screenshot and control the motion of the mouse. So 10 years ago, we would hack it through the ActiveX. Now we effectively have Python library that allows to emulate the mouse operator. So the way that we build the autonomous workflow for non-indentation, which doesn't have any API and the software is completely closed, is basically by hijacking the control from the human perception, and it works. It would work much better if it was an API, but you know, non-indentation is slow. So API can execute commands in milliseconds. Human interface can execute commands in hundreds of milliseconds. But for fundamentally slow experiments, that's perfectly fine. We don't care. So a lot of time that students in my group are spending is timing. How long does it take to execute this command? How long does it take to move the probe on the sample surface? How long does it take to send the data to HPC and get it back? So everything becomes about timing. If you don't know timing, then you cannot build autonomous workflows. But if you know timing, you know where to invest. So we don't need decision making 10 times faster than execution. We need it as fast as execution.
Hey, Sergei, Veronica Gustin from MSC. Thanks for the great talk. So I really like the example that you shared about the 4 competing hypotheses, because I think this happens a lot in material science communities. I know many instances in batteries where even though as scientists we don't subscribe to dogmas, there are always these kinds of things that, you know, kind of get perpetuated over time, that everyone thinks is the case until someone does an experiment to prove that it doesn't happen. And it seems like one of the really great things about the AI co-scientist would be that it maybe doesn't hold on to some of the biases or the things that restrict human scientists for saying, I might be wrong. And I wondered if you could comment on that, you know, where maybe that
So you are right that I would think about the large language models that they are now as the very broad but very shallow knowledge repository. So it will have the biases that were intrinsic to the data it was trained on, but these biases would be average across the community. So in this case, you know, the average is of course not necessarily the true average, but we can expect it to be much more representative of relative ideas, of the average ideas. At least we can use LLMs in order to provide the alternative hypothesis. The difficulty that I see now is that LLMs, for the time being, are trained on the human level language documents. We know very well that human language is not the intrinsic language of science. So, I mean, we can speculate what the intrinsic language of science is. It's kind of going very deep into the scientific philosophy, but practically we know that math has to be a part of it. We know that a lot of things that we are doing in science are certain level of abstraction, which is essentially model level, which is neither math nor human language, right? So when you hear, simplest example, imagine that you are attending the American Physical Society and you go in the room when people talk about lithium cobaltate, but these are people who are solid-state physicists and not battery experts. So all of a sudden they talk about the same material that you study for the battery cathodes, except they start to talk about the Hubbard use, spin-spin transitions, and all things like that. So human language is very diversified and deals with a lot of levels of abstractions between the essentially philosophy all the way to mathematics. For the time being, we have tools that work on the purely mathematical levels, and they work very, very well. So all the way from numerical schemes all the way to the deep learning. We have the things, or the pins and so on. We have the tools that work with the natural language, and we have no clue how to bridge this connection between the language of mathematics and the human language through the intermediate abstraction that become more and more tuned to the real world. There is a lot of things that are happening now in the fundamental ML community can be traced to that, like using knowledge graphs which formalize the human knowledge, using the connections in terms of physics, deep physics segmentation. But it's very clear that this started about a year ago, so we don't know what's going to happen in the next 3 years.
Anybody else ask any questions?
I was wondering if you could comment on, I guess with the reward function or loss function, maybe as part of it, of how to anticipate and avoid unintended consequences in discovery. And there's so many cases of materials or chemicals that served an engineering purpose, but then we find them in the environment in ways that, in retrospect, we could see why it's causing damage, but we didn't really think about it when we were doing the discovery of those materials.
So that's an excellent question, and I suspect that there is no fixed answer to that one. So risk assessment, as well as the serendipitous use assessment, is there is always uncertainty there, right? So it was a very famous statement by Paul Anderson that if theoretical models were correct, we wouldn't have to do experiment, right? So science always works on the feedback between experiment that discovers new things and serves as the hypothesis verification and developing of the theoretical models. The good thing for us as material scientists is that for the last 20 years, the ML learning tools that allow to work on experimental side were non-existent, and most of the investment went into the theory, which basically means that now we have a tremendous opportunity to build upon this investment and build the bridges between the theory and experiment, figuring out how to build the experiment-informed theoretical models and theory-informed experimental models. So there is an opportunity to connect. But there always would be unexpected consequences. So we can, for example, for microscopy, the concept that we're working with is guardian angel model. So the guardian angel model is supposed to observe the human or proposed human OML operations and raise the yellow flag, which says that maybe you shouldn't do that. There has been incidents when this operation led to crashes, or you absolutely should not do that. That being said, I can build the ML agents that do stuff on the instrument, but I know very well that in order to build the guardian agents, I need to work in the industry because I need to have access to the enterprise level knowledge about the tool and the ways it went wrong. For anything related to material synthesis, it is the same story. It is fairly difficult, very easy to build agents that will discover someone trying to use your automated lab to synthesize a neural agent, because these have a very characteristic signatures. But if somebody comes up with a quote-unquote brilliant idea of how to make a transfer of function from some form of flu virus, for example, maybe it is easy, maybe it's complicated. It would be an area by itself. So it cannot be the rigid prescription, because once you define policies, it's like socialism. If everybody is supposed to work in the lockstep, you're not going to get far. But ensuring the security of the automated labs is an important thing, and it's an area by itself, and it has to be done. And it will never be done in a 100% reliable way.
There's one more question. One quick question.
Hi, do you envision a workflow where you have both a reward and a penalty, and if both of them will beat against each other at any point?
We can do that. So once you have multiple rewards, or you switch between the different rewards, like learning something about material, optimizing the microscope, there is always a question of how do you balance them. And that becomes essentially the optimal planning. In order to do that, you need to have the total objective rather than local reward. And basically, the fundamental framework for doing that exists. It's called the stochastic optimization. So the areas that come closest to that is something like supply chain monitoring or stuff like that. So these guys know how to define these workflows if they know the reward function. In science, it becomes a little bit more complicated because I typically have a long-term objective. So this is something that motivates my work, and this is what I write in my introduction to my proposals and papers. I usually have explicit or implicit the short-term reward because I need to tell myself that, okay, now experiment is successful or things don't work out, it's time to go home and drink beer. But the intermediate rewards that's required for the intermediate planning are not that easy to formulate. And I suspect that there would be a whole science of how we do that. Predictably, this will probably come from places like Google and Facebook for problems that have nothing to do with materials. But, you know, I mean, we do with what we have, right?
Well, thank you very much for the informative and nice presentation, Professor Kalinin.
Thank you.
Let's give a warm